picking up where we left off, before we get to the next example, I wanted to present you guys with the way I break down a related rates problem. So I call these the related rates steps. Four of them. We did all of these in that example with the ladder sliding down the house. Let's take a look. Number one, make a drawing. Typically, this is going to be critical. You have to make a drawing in order to make sense of all the information they tell you. There are some easier variety problems where you don't need a drawing. We're not going to do any of those here, but you will see some of them in your homework early on. They might talk about, like how fast the area of a circle is growing. Like, well, we don't need a drawing of a circle to make sense of, what's going on. We're familiar enough with circles or maybe spheres. And so that's not maybe going to be necessary, but usually in a typical problem, like the one we just did and what we're about to do, a drawing is critical. Labeling it carefully, labeling the quantities that are changing with the variables, labeling anything that's not changing as a constant, and then noticing like, oh, I've got a right triangle or whatever it might be. Okay. Step two, from your drawing, find an equation relating the quantities. Okay, so we did that right. Once we had our triangle, we're like, oh, Pythagorean theorem. Usually step two is the most difficult step to achieve. Once you have step two, then it's just a matter of going through the rest of the steps, taking derivatives, and then figuring out what numbers to plug in. If you can get step two, you're in a really, really good position. And it's not uncommon to spend 50%, 70%, 90% of the energy is just trying to figure out what the equation is in the first place. Very common. And that can be frustrating because I can't even get to the equation. So just realize that's what makes this section challenging. They don't give you an equation. You got to come up with it on your own. Okay, number three, once you have your equation relating your quantities, then you take the derivative of both sides with respect to t. Okay, and we t because it represents time. Things are changing in time. So you'll take your derivative of both sides there, your implicit derivatives. And then number four, find the unknown rate, identify what they're asking for, right? In the previous problem, we could tell, oh, they're asking about dy over dt. So identify which derivative or which rate they're asking about. And then okay, I can plug in a number for all the other ones, the other known quantities and rates I can find from the description of the problem. Plug those in, solve for the one you want, boom, you got it. Okay, let's dive in to the next example. This example may look familiar if you recall the What is Calculus intro video from 3 weeks ago. Only 3 weeks ago. Wow. It's the Ferris wheel. Okay, so example, a Ferris wheel with a radius of 10 meters is rotating at a rate of 1 revolution every 2 minutes. Okay, seems reasonable. Got a pretty big Ferris wheel here, and riders go all the way around, so your ride on the Ferris wheel is 2 minutes. Okay, how fast is a rider rising when he or she is 16 meters above ground level? Round to 2 decimal places and include units. Okay, so let's picture this. So we got the Ferris wheel, pretty big, and they're at the moment in question, they're 16 meters above ground level, and picture they're keep rising from there, so they're almost on the way to the very top. Okay, so here's my drawing. We're going to add more to this as we talk it out. So I've got my Ferris wheel, and what I've done, the ground level, it's assumed to be right at the level where you get on the Ferris wheel. So a lot of times Ferris wheels, sometimes you'll see them where they dig out, like the ground is lower underneath so the Ferris wheel can pass through, and you actually get on at ground level. So that's what's happening here. And then our radius of our Ferris wheel is 10 meters, and they're up about here. So, they're past halfway, they're on their way to the top. So that's kind of a good, we could draw this anywhere and that'd be fine, but this really fits the description well. And we can also label that this is 10 meters, right? It's still the radius, so that 10 is fixed. It's not changing. Okay, so what can we add to this drawing? Because we need to get in some variables and label the pieces that are in motion, like changing, right? Okay, so as this rider comes around, as they come around the arc, they've got a vertical motion and they've got a horizontal motion, right? So they're moving up and to the left simultaneously to get to the top. We only care about the vertical motion. How fast are they rising? So yes, they're moving sideways as well. We don't care about that. Okay, so what's going to be key here is like, what do we even do with this? Here's what we can do. We're actually going to create a right triangle again. So from the center point, draw this right triangle. Okay. And on that triangle, we can say, okay, so how fast are they rising? We're going to label this length here as changing. That's a y. All right. Makes sense to use y. It's a vertical distance. All right. We can also label this angle. I'm going to call it theta. So this one's working a little bit differently than the previous problem. If we call that theta, well, isn't theta changing, right? As they rotate, that angle gets bigger. Why not? It doesn't have to be a linear distance. Angles can change too. Angles can move and get bigger or smaller. Okay, so we've got this right triangle. We've got theta. We've got y here. We've got 10 right there. This is all we need. Can you think of a way to connect theta and y, and the 10 will be involved as well? Can we connect theta and y in an equation from all the math you've ever learned? Think, well, yeah, I think we can with some trig, right? Theta, opposite over hypotenuse. Isn't that sine theta equals y over 10? Perfect, we've done it. We got the equation. That's the hardest part. And it really came from that drawing and realizing that angle is changing. Once you had that, then the equation was right there. Okay, so sine theta equals y over 10. You know what? We're going to take derivatives, but maybe I write this a little bit cleaner, a little bit simpler for derivative taking. Why don't we think of it as 10 sine theta equals y? Hey, it's an equation. I can multiply that 10 over here, and that will make my derivatives just a little bit easier. So 10 sine theta equals y. Perfect. Now, let's take the derivative of both sides with respect to t. Okay, so with respect to t, what's that going to do? Well, on this side, we'll have 10 cosine theta, but then we need that chain rule on theta, so we're going to multiply by d theta over dt. And on the right side, there's not much the derivative with respect to t is simply dy over dt. Okay, looking good. Let's see. Now, once we have the derivative of both sides, then we need to go back and read the question again and make sure that we are looking at which rate are they asking about. Well, it says how fast is the rider rising when he or she is 16 meters above ground level. So it's the dy over dt, and you can probably see my little arrow down there. Let's scroll up here. The dy over dt, the rate of change of y, of course, describes how fast they are moving up. So this is what we want a value for in the end. So it must be that we can figure out the values of the other two unknowns, the theta and the d theta over dt. Okay. I wish I could fit all this on the screen at once. We are now here. Okay, so if we can get these two values, boom, we got it. We plug them in, we're done. Let's see here. I'm just going to pull this down and then talk you through it. I'll show you all of my work here for both. We realize that they only tell us a couple things, right? So we know that the rider, let's start here. We know the rider is 16 meters above ground level. So we can say that y equals 6, right? If they're 16 meters above the ground, then, well, this is 10 meters up. At the moment in question, y equals 6, because they're now 16 total meters above ground. Okay, great. So if y is 6, problem is we don't have a y. And it's just the way the derivative worked and the way the equation, it all came together. We don't have a y to plug in, a 6, right? There's no y here. So we're not going to plug the 6 in, but it's still helpful. We still need it. We need it to get theta. So if y is 6, and we know that the sine of theta equals y over 10, then we can say the sine of theta equals 6 over 10. And then to get theta, well, we just take an arc sine, and I went ahead and reduced 6 over 10 to 3/5. So we know theta equals arc sine 3/5. And I'm comfortable just leaving it like this because I know we're going to round the answer in the end anyway, and I've got a calculator, no problem. Okay, so that's what we will put in for theta in another minute or two. What about d theta over dt? Now this is interesting, and this is tough. What else did they tell us in the problem? So they told us they're 16 meters above the ground. Perfect. We used that already. They also told us the Ferris wheel, radius 10 meters, okay, is rotating at a rate of 1 revolution every 2 minutes. So this thing goes all the way around in 2 minutes. That's talking about an angle. That angle goes all the way around in 2 minutes. That's telling us how fast theta changes. So how can we use it? Okay, let's look at the details. 1 revolution every 2 minutes. So if you think of d theta over dt, that's the revolution, that's the time. So if it goes through 1 revolution, that's 2 pi radians. So it goes through 2 pi radians every 2 minutes. 2 pi over 2. So d theta over dt would reduce, well, just to pi. Pi radians every 1 minute, if you simplify that. How fast the angle is changing. Okay. Now that's tricky. That's hard to catch. Now, but you kind of take advantage of, the Leibniz notation and the units, right? Well, what was the theta? Well, theta went through 2 pi. What was the time? 2 minutes. Okay, 2 pi over 2 minutes. Boom, reduce it. Pi. All right, we're ready. We're going to plug it all in. So I'm just repeating our related rates equation there. And now we're plugging in all of these things. 10 cosine of inverse sine 3/5. All that times pi, that will equal dy over dt. Grab your calculator, make sure you're in radians, and put all this in. And you should end up with dy over dt equals 25.13 when you round to 2 decimal places. And then we think, okay, so then what are the units? Well, y represents meters, t represents minutes. So meters per minute, 25.3 meters per minute. And we got it. Now, this answer works. It's true. We got it. However, it doesn't really give us a sense of what the person is feeling, right? 25 meters per minute. Well, 25 meters is what? It's about 80 feet or so, 75, 80 feet. So to move vertically 75 or 80 feet over a minute, I mean, a minute's a long period of time, and that'd be a long distance vertically, right? 75, 80 feet vertically is a lot. So while this makes sense and we definitely have it, maybe we'd like to answer in like meters per second. That would give us a better sense of what the person's experiencing riding in this Ferris wheel. So I went ahead and divided that by 60, just because that it seems like a better fit for this context. And so when you divide that by 60, you get 0.42 meters per second. You're like, oh, okay, so in the next second, they travel a little bit less than half a meter. You're like, whoa, half a meter in a second, like, is that a lot? Like, seems like a lot. Maybe it's not, but just kind of my own experience. We have a part B to this one as well, but when you're going in a Ferris wheel, it always felt to me like you're moving a lot faster when you're at this like perpendicular point to gravity. When you get to the top, it feels like you're moving slower than when you're out here. It feels like you're moving really fast out here, and you start to slow down up here. Actually, you're moving the same speed the whole time, right? But there's so much vertical motion out here, and still at this point, there's a lot of vertical motion. When you get to more horizontal motion, you start to level off. It doesn't feel like you're moving as quickly, even though you're moving the same speed the whole time. Okay, so what's part B? Hey, let's explore that. How fast is a rider moving horizontally at the same moment? So all the same scenario, they're still 16 meters up, but instead of moving, how fast are they moving vertically? How fast are they moving horizontally? Well, it turns out we've done pretty much all of the hard work. We just need to go back and change a couple of things. Okay, so I've got the picture again, although you could use your same drawing as in part A. We've got the circle, we got the ground level to 10, 10. I'm going to create that triangle again. Still labeling theta, but this time instead of labeling the vertical for the vertical motion, I'm going to label the horizontal because we're going to think of this motion here. Okay, so this, if that thing continues up, then this distance on the triangle is going to shrink. And we've got that horizontal motion. All right, so let's see, how are theta and x? What's an equation connecting them? Like, oh, well, that would be cosine, right? And I think I'm going to reveal my answer out there. I'm just going to show you everything, and we'll talk through it. Mine as well. Okay, so cosine theta equals x over 10 from the drawing, the triangle. Same idea. I'm just going to multiply this 10 over to the left side. Just makes my derivatives go a little bit smoother. And then we'll take derivatives with respect to t. So cosine is negative sine. So I could just say negative 10 sine theta d theta over dt is equal to dx over dt. Now I know theta, it's the same theta. This is at the same moment as part A. So I can still put in that same theta that I had before. Arc sine theta 3/5. And I can put in the same d theta over dt as before. Actually, that wouldn't matter at what moment we're doing because that's just the speed of the angle always. But okay, those will be the same. And now it's equal to dx over dt. So if I put all of this in, and even notice sine of the arc sine, these would cancel. You know, we could cancel those out if we wanted or whatever. Okay, anyway, so it's negative 10 times 3/5 times pi. Should get you negative 18.85 meters per minute. And again, we have this thing with the negative, and we could have expected that from the beginning. X is shrinking, that distance is shrinking, so we think of the rate of change as negative. Although we're not really concerned with negatives and positives, although they make sense mathematically. What is the writer experiencing? Well, you could answer as the positives. You could answer this way. You could answer as the positive version, 18.85 meters per minute. Or what might be even more appropriate is to divide this by 60 and say 0.31 meters per second. And that'll do it. Okay, that is our second example. We got one more coming up next.